Good evening all. So what I'm going to talk about now, this is a novel apps paper. So we have an application that has been developed at IBM. So this is basically for scheduling of activities in iron ore mines, about moving the materials from the mine to the port. And this is the work that was done together with IBM Research in India. Me and Alfia from IBM Research, and we have the IBM Software Group, ILOG Group, Alan, Julian, and Fabio from France and Spain. Okay, so what I'm going to do here is, like, I'm going to start with the business problem, what's happening there, then I'm going to formally tell the problem description, and also then the solution approach at a very higher level, what we are doing there. And then the last three parts, the implementation, visualization, and the application scenarios, I'll quickly browse through in a few minutes because we have a demo of this following this. So where I can show more clearly what we have done with this, this specific asset. Okay, so what's the business problem? The business problem, as I told, this is about the iron ore mining. So people extract. What actually happens there? They extract the bulk material, they process it, they stock it, and then they move it by rail to the port. And at the port, then again they load it onto the ships, and then it reaches to the customers. Now, as all of you would be knowing or be aware that this is a very profitable business. So somebody was telling that whatever that's around like $15 worth of material they are digging up and moving, they sell it at the market for $165. So so they happen to be very rich. So what happens is that they kind of own the entire supply chain. So they have, every mining company have their own ports. Every major mining company have their own ports. And there are some few companies which do not own the rail network. So they use the third-party services. So in many cases they own the end-to-end stuff. And so what we are actually going to look at here is the end-to-end movement of this, the material here. So basically what happens here is that start digging from the mine, and then you put it on the train, move it to the train, and there's a lot of stuff that happens in the stockyard. Where this train gets, the filled up rakes get dumped, and then they are kind of stopped into stockpiles, and again they are removed from there and put in the machine. So this is a kind of sequence of interdependent, interlinked activities done by very large machines, and these machines are like expensive, large ones, so we have few of them, there's no redundancy. And this is how the entire operation works. And there are, of course, inventories in the middle. So like, for example, the inventory at the port can handle some 2 to 3 days of your demand, but not more than that. So if anything goes wrong on the way, or if something goes wrong, you should be able to immediately revert back to the normal operations. The scheduling. So there's a guy here who does it on an Excel sheet or a computer program that does the planning and scheduling. Now, when it goes to the operation, that's what we call as execution. There are people who are going to implement the schedule. So there are a lot of discrepancies in the way it is done by an off-the-shelf software than when it's being executed. And we have another group called the maintenance. So these are the people who go and take care when something goes down. And they also say that, hey, I have to suddenly make sure that I have to make this car number work for next few days. So these two guys don't talk a lot. They optimize things locally. And only time they talk is about, you have not done this properly. You have told me this before, kind of a scenario. So what are the goals of the overall asset, the application? The goals is that first minimize the penalty, the demurrage penalty, and not fulfill demands. So if you look at the entire process of the movement, the way where you actually count the value in monetary terms is when you get fulfilled the order at the port, when you load it onto the ship. So there are a lot of things that happens wrong there. For example, the ships get delayed, they have to move, but you keep on loading, so you pay a penalty for that. Or you are unable to satisfy the demand you have accepted. Okay, so this is directly the money value. And then you have other soft goals like you integrate the production, operations, and maintenance, because that cannot be immediately measured, but over the long term it has a lot of effects on your things. So what you have to take into account are the things like I have to take into account the work in progress. I have to ensure that the rolling horizon is kind of seamlessly taken into account, and also the concept of dynamic rescheduling. If something goes wrong, how do I shut down the operation without much thing? I'll be able to quickly come back to a new schedule. Okay, so let me explain put the problem description here. So, okay, first and foremost, what's the scope of the problem? Well, that's the entire supply chain, but our scope starts from the mines. I have the materials already there. So the supply is kind of fixed because the planning horizon we are looking at is like 2 to 3 weeks. So that's when you are, this is all dependent on the ships that are going to arrive, and I'm going to load them onto the ships. So I would know very clearly only for next 2 to 3 weeks the exact arrival and the departure of the ships. So that's my planning horizon. So what you're talking here is about the operation scheduling, right? So in which case, I can assume that the supply is given to me. The mines have already done and they have a supply schedule. I'm going to follow that. And I don't care once it is loaded onto the ship. So what is given to me are the demands. The ships are coming and I have to choose them. And then I have the on-hand material availability at different points in the supply chain and what is my rolling stock, etc., where my trains are, how many trains are there. And then I have the supply schedule. Now I have to determine the scheduling of end-to-end activities. So I have to decide how do I load the trains, what time I load them, how do I send them, then what kind of dumping and loading happens. So usually this is done. So you have off-the-shelf softwares for doing all these things at different places. So for example, the softwares to handle just the berth allocation and the scheduling problem. You have something for stockyard scheduling, you have rail logistics, these are separately there. What we are looking at here is something that is end-to-end because this is a very good way to attack because this is owned by a single company, so you could do this possibly here. And so you want to do it end-to-end, and in that way, things become more seamless and optimized. Okay, what's the material flow? The material flow is like, okay, the supply is given to me there, and from there, I have back and forth rail movement, but of course the reverse is kind of empty, so I have this is the bulk ore, right? So which is like a continuous material. So at the mines, it is like almost like continuous, my inventory. The moment I put it on the transportation for the rakes, it becomes in the kind of discrete quantities, which moves there. And once it goes to the marshalling yard, stockyard, and ships, they are all at the port. So once it goes to the port, the inventory is in the form of discrete units called rakes. Then there are two activities that happen at the stockyard. One is called the dumping, that is from the train you put it onto the stockpile, and another is the loading. From the stockpile you put it onto the ships. And so there are several issues here, basically because the stockpile is a shared one, and many times the stacker and reclaimer are the same equipments. They just work in different modes. And there will be a lot of access restrictions with respect to which stacker can access which stockpile and kind of things. And of course, and one more thing here is that there are multiple materials that are flowing through here. It's not just a single material. So the stockpiles have different spaces for putting these materials here. Okay, there are a lot of planning and scheduling decisions and activities that have to be taken in this one. So as I told that if I try to enumerate, it's kind of quite large. But you can safely assume that the kind of typical constraints you see in the scheduling, like all your precedence constraints, no overlaps, and the inventory constraints with respect to the planning, all this stuff's kind of come here. So if I want to just give a very brief idea of what happens at the port, so that's basically a berth allocation problem, and you have to select there will be constraints with respect to the compatibility of the ships versus berths, and you will have a sail out constraint for high tides. So it's filled with a lot of things that can be that's kind of interesting here. Okay, so what we have finally end up with? So we end up with a kind of a multi-stage scheduling problem, which are kind of individually hard. But the good part here is that this is not a very large problem, right? In terms of data, it's not very large because luckily all these equipments are so huge that you don't have hundreds of them. So you have few of them, and it's a movement of large bulk material, which takes days to happen. So it's not like something like you're switching packets per milliseconds. So that's the good part about it. So the problem is not large per se, but it is the complexity arises out of this because of this interdependency here. So even though these problems are kind of individually hard, if we can handle them, kind of in a bit of an intelligent way, then they are useful for all practical purposes, and that's what we have done here. And so this rail logistics is again a very tricky part. Usually, as you know, that the rail logistics could go up to the level of controlling the sidings and the arrival of the stuff. So you cannot go to that level when you do a kind of a commercial software. So what we have done is that it's actually at a macro level, at the two levels of macro, we can say. If the company is not owning the right network, then it's more about at the level of things like, okay, every 6 hours, how many trains I can send from here to here. And another is about scheduling the trains with constraints like what is the gap between any two trains and what is the line capacity, etc. But not up to the level of the control mechanisms. Okay, so what do we have here? So I'm from a mathematical programming background. So what do I see here is a large problem with a lot of scheduling constraints and also a lot of planning constraints. So if I'm trying to go into a single monolithic, mixed integer linear program, I mean, it will be kind of humongous in terms of the number of the auxiliary variables I have to reduce into the problem. And also it's not very advisable given that if anything I have to change in the later part, I have to go and change the entire code. So what I need to do is something that I have to make it more modular and decomposable. And there are a lot of other activities, other problems which we are handling through that's outside the optimization mode. Okay, the two ways to take the modeling complexity is that you do a kind of hierarchical decomposition. That is, I do a planning and then I do a scheduling. I fix the higher level activities, then I do a final level activities. Or otherwise, what we do is that we do across the stages. I fix first stage, then I fix the second stage. In any case, you have to worry about how these inconsistencies between these things are handled because you're not doing them together, you're doing them separately. Okay, so what we have done is actually a kind of a decomposition which is hybrid in nature, and also we use both math programming and constraint programming in solving the problems which are relevant to each of these things. So this is the overall decomposition. So what we do here, as you know that I have the supply, I have the demand. The supply is fixed, so I'm not going to touch it. The demand on the other hand, which is the ships that are arriving, so I have to schedule the ships, so that which is very much equivalent to scheduling my demand. So that's like a pull network. Once I fix that, then I can decide how much to push from here. So in the first problem I solve is fixing the demand. So once I fix the demand, then I do a kind of a detailed planning about how much to maintain at each of the inventories. So this is kind of a higher level plan. Now, given that plan, what happens in number 3 and number 4 are the actual scheduling. So I do a scheduling of stockyard separately, followed by a scheduling of trains. Now, a lot of things could go wrong in the 3 and 4 because I'm using a lot of higher level parameters on the top without taking into account the finer details of the components below. And I do the plan. But once I start doing, so now how it happens is stockyard scheduling happens. So I have to exactly know where my equipments are there, what status in condition they are. So there will be a lot of inconsistencies that could go wrong. So what we do at that point in time is to solve, we have inconsistency resolution module that kind of iteratively solves this thing and finally comes up with a solution that is consistent from the beginning to the end. So in that sense, if you look at it, in some ways you can think of these first two problems as the planning problem, even though the first one is more of a scheduling, it's demand scheduling, but still I could think of this as a planning problem, and which drives my other two scheduling problems. So we have kind of a hierarchical decomposition here, and also the things that spans across the stages. Okay, and so the way we have done is that the first problem we have used the constraint programming because it's full of logical constraints, and the second one is MALP. Again, and third and fourth are the constraint programming. Okay, this is where we solve the interstate inconsistency resolution. Okay, so let me go. So how we have implemented this? So this we have implemented in what's called as an ILOG ODM enterprise. So most of you would be aware that ILOG has this solvers called ILOG solvers solve simplex, which is the MALP part, and also the CP optimizer, which handles the constraint programming part. So that's more like what researchers do at academic level or what we try to do with some problems. But when we talk about building a solution around it, so what we need is the other things like data layer, visualization, and kind of stuff. So what happens here is that what you see here, this is what usually we try to do. The optimization models is OPL, but this has all the other extra features that is required thing, so where you can build an application. So this is basically done together with, so many of the features like the post-processing and the pre-processing, like how do I extract the work-in-progress information, how do I extract all these things are done externally and then fed into the optimization model. Okay, so we have a lot of very nice visualization things that can happen here. So for example, we can, so here it says that there's an order and it tells from the beginning like how this material has moved. Now, actually this was not done in the optimization. So while optimizing, we really do not care about which order we are going to satisfy. We only want to know what is the next stage and I move it. But of course, a customer wants to look at how things are moved, so if anything goes wrong, how it can be taken care of. So this is kind of a pegging logic that is done externally afterwards. It's a post-processing to create a figure like this. Then they can look at the material availability. Then again, you have this visualizing the entire plan and the Gantt chart, the standard issues that you do with the scheduling stuffs. Then you can also look at the material movements. So here is another thing about how do you visualize the work in progress and the maintenance. So as I told that, one of the most important things is to close the gap between the planning and the execution. So when I go to, I never always start with a clean slate, right? So always there are activities that are going on. So how do I extract the work in progress information and feed it to the optimizer in such a way that it can be resolved perfectly? And then there are things like most of the times, this is again another requirement that it goes out to the people on the field for executing, and they may want to manually edit my plan. So in which case that you manually edit the plan, so if there are some errors it shows, if it is solved, okay, it is fine. And then after editing you can again resolve it to ensure that whatever the user has wanted, it has been taken care of. And so basically these are the different views. So most of the leverage penalty and the bonus is basically what the customer really wants to look at. That's the money part. They always not care about that. But there are the other things which are kind of internal to the engine, which solves and so as we have 4 models, so all these 4 models work at different levels and they give the overall combined thing to the objectives. Okay, so there are different application scenarios we can see here. But one of the major assumptions here is that, so this is basically a plan, execute, monitor kind of situation. So you need to have a very good monitoring system that is going to give me what is currently going on there. So otherwise, so basically, so how do we resolve uncertainties here? We do not do a stochastic programming, or we don't take into account the probability information or something like that. What we want to do is, when something goes wrong, how do I quickly react to it? So in which case, I have to know exactly what is going on at that point in time, so that I have a very good information of what is going on, so that I will be able to resolve. And so we assume there is a supply chain execution and a monitoring system out there, which also IBM has, but we assume that they have it. And then once we get the status, so there are a lot of other things that can go wrong, and we'll be able to reschedule and get it in a very quick way. The different use cases could be the normal rescheduling, where you take into account WIP and do all the things. Another thing is unforeseen disruption and deviation. So something goes wrong. So I'll show all these things in the demo. Then you could take the disruption event and create a new schedule. And you can do this proactive maintenance. So the maintenance guys comes and says that, next 2 days I want to put this machine down for 8 hours. So you take that into the schedule and do that. So that is another possibility. Another thing is the manual editing of the plans. Okay, so what I would have been very happy to show you is some kind of results in terms of how it performs with different sets of data. But unfortunately, as you can appreciate that it's very difficult to have a standard data set to solve against here. But we do have some data set where I will show this the applications. The overall time is around 5 to 6 minutes. The entire solution process, how it shifts from one model to another. The overall thing happens in 5 to 6 minutes. For a very a thorough academic kind of evaluation, we don't really have. I think that itself is another big work to do. Like what kind of data set we should take, challenge sets that can challenge this problem. Basically, because many of the things have to be worked with respect to, you have to specify each and everything. I mean, where my rakes are, where my trains are, and that could be, they could be in so many hundred possible ways. So for us, it's not just changing the supply pattern or the demand pattern, but the pattern of the entire system throughout, which makes it much more complex. But anyway, I can, I'll be happy to answer some questions. But to do overall, what we are trying to do is that we have, in many ways, we are trying to make all this, the three guys kind of talk to each other in a much, we are close to the loop between the, the planning, execution, and maintenance. So that's something that has been achieved here.
Okay, thank you.